All right. Hey there, everybody. Today we're starting 10.1. I will probably make a video for 8.4. It's not going to be on the test for sure, because it's really not. It's a differential equations topic that comes up in Math 81, where you will do it much more better and thoroughly. So I don't even know why we do it in Calc 3 or Calc 2. But 10.1 is of utmost importance. 10.1 is on parametric equations. And at least a good 2 whole chapters of Calc 3 uses this, if not more. Like it's of absolute importance. So what we do is we will have like y equals f of x. And we are going to treat x as a function of time. Which kind of makes y a function of time also. So like x is now x of t, and y is y of t. How does this relate? You're driving, you're going down to Disneyland. We could have a path, if we like overlaid a map of the Earth on a grid, we could come up with some like line or equation that gets us there. But the parametric equation or version of it shows us which direction on the line you're traveling. So graphically, there's 2 ways of going about doing this. Graphically, it shows the direction of motion. Which is important. Calc 3 is 3D, and so like it's basically necessary for all of physics, and physics has a lot to do with motion and shit like that, so direction matters. So let's just look at a couple examples, graph them out. This is a common one to start with. X equals cosine t, y equals sine t. So I'll pick some values that are kind of important. We got 0, maybe pi over 6, pi over 4, pi over 3, pi over 2. And if we plug these in, we get 1, 0. We get root 3 over 2, which is 1.7-ish over 2 is about 0.85. And this is sine of pi over 6 is 1/2. These are both root 2 over 2, which is approximately 0.7. Pi over 3 gets us 1/2 on this one, and root 3 over 2 on this one. And pi over 2 gets us 0 and 1. This is the table you learned in trigonometry, if you took it. We just didn't use t, we used theta, right? What's going on here? At t equals 0, I am at 1, 0. And let's see, at t equals 2, I'm at like 0.7, 0.7 is right about there. Let's see. Not t equals 2, t t equals pi over 4, sorry. At t equals pi over 6, I am at 1/2 up and like right about there. So that's like t equals pi over 6. T equals pi over 3 is right there. And we get to t equals pi over 2, we're here. So the direction of motion is in that direction. We're following the time. And you'll notice that the distance traveled doesn't necessarily, well, these aren't equal time steps, so that's a hard example to do. Never mind, don't want to use that example here. So what does this look like it's making? If we do the full circle, it will keep going around and circle around. And at 2 pi, we're back to where we started. So we're going around the unit circle in clockwise motion. Counterclockwise. Backwards. Clocks go that way. Clock go that way, and we're going that way. I realize I'm doing like this, and from your guys' direction, I'm doing completely backwards. Now, there's a couple ways of seeing what this equation is. It sure as hell looks like x squared plus y squared equals 1. Well, is that true? Cosine squared t plus sine squared t. The other way of doing it, you can't always recognize something like this. The trig there is helping us, but we can always solve like one of the letters for t and plug it in for the other one to get y in terms of x. So if I said t is cosine inverse of x, then y equals sine inverse of cosine, not sine inverse, sine of cosine inverse of x. And we got to make a little like that triangle here. Cosine of t was x, which is x over 1, which is adjacent over hypotenuse. And if we use the right triangle, we're going to see this should be 1 minus x squared. Right? If I call that c, x squared plus c squared equals 1. So c squared equals 1 minus x squared. And we get c is that. That is using this as t. So t was just like our theta. And now if I'm doing sine, sine is opposite over hypotenuse. And if I squared both sides, I can see I would get that. What are you looking at, Michael?
Health one is killing me hard. Hashtag health survivor crossed out victim.
Calc 1 does take out a lot of students. It's generally underprepared, or it's been too long since they've done the algebra and trig and have forgotten it. How a lot of students hit it. Even the ones that thought they were prepared. If you only do 3 years of math, or even worse, 2 years of math at high school, you've taken 1 or 2 years off. That's a long time to not do something that you're going to need to like remember the fine details of. All right, let's look at another one. Let's do x equals t squared and y equals t cubed. I'll make a little table. I'm going to do 0. I'm going to do 1/2 just because I want to see what happens between 0 and 1. And then maybe I'll do 2. Trying to look at what's going on here. And maybe we could look at -1. See what's happening as we go negative. Time doesn't have to start at 0. We could go what happened previously. So if I plug these in, remember this is t squared and this is t cubed. I get 0 and 0. 1/2 squared is 1/4, and 1/2 cubed is 1/8. 1/8. 1 is 1 on both of them. This is 4 and 8. And this is 1 and -1. Oh, that's crazy. And when we're doing it in order for direction, this is really above that. So we'll put in the t -1 first. We're at 1 and -1. Then 0, we have that. And then t equals 1/2. We have 1/4, which is not very far along, but even lower down, like really low. So that's like t equals 1/2. T equals 1 is right there. That looks like that's doing some shit like that. And when I do t equals 2, t equals 4/8. And it's going that direction. Which means it's probably coming in like that from that way. Interesting looking graph, kind of like throwing a ball upwards and it just bounces off the wall. Like if gravity were going to the left. That's what it would look like if I rotate it like this. It looks like we threw a ball leftward and it fucking hit the ball ground and bounced to the left, but like bounced higher than it should kind of thing. If we want to see how that looks, we can solve this. Let's see, x equals t squared. So if we take the square root of both sides, we get t equals plus or minus the square root of x. And if I plug that into y, I get y equals plus or minus square root of x cubed. This is like plus or minus x to the 3/2. So this side up here has got to be the positive one. And down here would be the negative one. Not too bad so far. It's a little different. This is really just the algebra part. We haven't hit any calculus like yet. But let's make sure we're comfortable parameterizing before we start trying to take derivatives and shit. Let's try. Why don't you guys try your hand at x equals t plus 3, y equals t squared minus 1. And let's do this for t in the region 0 to 3. Take a couple minutes, work that out.
So what work the ours have like, is there a meaning behind that? Or-
It's because I fucked up. Thanks for calling me on my shit.
I was just like, is that math notation that I don't know, I should know, or is it like?
This up here was like for all t. I didn't specify that. Here, we're gonna limit it. I would. Unless you're a psychopath. The only reason I did this is because I wanted to kind of see if it was coming in to like bounce off or like do like a curve. You know what I mean? Did we get a cusp on the graph or not? I like increments where the numbers are whole numbers personally. We got a lot to do today. We're gonna do derivatives, we're gonna do tangent lines, we're gonna look our favorites, arc length, and even better surface area. Holy shit. This is just a busy fucking day. Yeah, that arc length shit just doesn't go away. This bastard put it on your test again. How rude is that? It must be like it's important or something. Wait till you start doing it in 3D. Then you can't even picture the fucking arc length very well. You can't draw very well. Well, I can. Some people sketch pretty well. Would you believe there are some teachers that teach Calc 2 that have never taught Calc 3? So like they don't remember how important some of this shit is. The glory of it. This is like this is the shit right here. if anyone's interested in working on some math over winter break, just to make sure you stay fresh, I'll give you guys a list of topics to like study and review. Some people like to do it. Not everybody does, but it's good to not take a month off, even if you only do a little bit each week. Keep your mind in the game. I have no idea what these answers are. Let's see. 3 and -1. 4 and 0. 5 and 3. 6 and 8. 3 -1. 4 0. 5 3. Ooh, not going in a straight line, is it? 6 8 is up there. And I'm going to connect the lines and I'm going to show the direction of travel, but I'm not going to extend it past it because it just said t equals 0 to 3. This would be like us driving to Disneyland. You don't keep fucking going. Once you get to Disneyland, you stop, assuming that was your destination. This looks like it's doing some parabola shit, and that actually looks like it might be the vertex. It looks like it might be doing like a regular parabola, but how could I find out what the equation is in terms of y and x? We tend to like to write y by itself, so it's often good to switch the t in the x one. So if I did that, I would subtract 3 from both sides. And that's t, so when I plug it into t squared, I have x minus 3 squared minus 1. Yep, that is a parabola with a vertex at 3 -1. So if it were to keep going, it would have kept going like that, and it would have came over and gone like that. But we're only looking at the red component. You guys ready for some more? Let me give you guys another one to do. X equals 4 sine t. Y equals 3 cosine t. And let's go for t from 0 to 2 pi. I'd probably go in increments of pi over 2 if I were. Let's see, 0.03, that's t equals 0. Looks like we're making an ellipse, right? And we're going clockwise. And then I went to 40. It's going this way. 0.3 is right there and 40 is right here. We see this normally when you have cosine related to x and sine related to y,
Yeah.
by switching it up, it's actually changed the direction of travel. And this one doesn't look like a lot of fun. But if I say x over 4 equals sine t, I can get a picture. This is angle t. Opposite over hypotenuse. I say that's c squared plus x squared equals 16. So c equals square root of 16 minus x squared. And we got t equals sine inverse of that. And when we plug that into y, we get y equals 3 cosine of that. And cosine of that is square root of 16 minus x squared over 4. So let me make this look a little bit prettier. And we'll make it look like an ellipse. First off, I'll clear fractions. Then we square both sides. 16y squared equals 9 times 16 minus x squared. Which is negative 9x squared. I'm going to leave this as 9 times 16 because I remember how the equation of an ellipse looks like. If we need to multiply out the 9 and 16 later, we can, but I don't think we do. Add 9x squared to both sides. You get 9x squared plus 16y squared equals 9 times 16. And divide everything by 9 times 16. And we get x squared over 16 plus y squared over 9 equals 1. Which gives us the equation of the ellipse we had above. It's probably been a while since you've worked with an ellipse equation, right? So how does that compare? This is like x, oh, that should say squared. X squared over 4 squared plus y squared over 3 squared. This is telling you the length of the major axis or the radius of major axis, or x-axis, I should say. It's the major one here, but that's like the radius along y. Radius isn't the right word, but now I do want to point out something, looking at the two graphs on the top of these two pages. On this one, when we went from t equals 0 to t equals 1, we went from 0, 0 to 1, 1. Then a single time step more, 1 second later, we jumped to 4, 8, all the way up here. So the amount of distance covered was not uniform. It wasn't equal each time step. Right? Here, it kind of looks like it is. Every pi over two, we made it a quarter of the way around the ellipse. So you can't always tell by looking at it if t is going to give you equal steps along the graph. Make sense? It's like it gets faster or slows down. Everybody good with parameterizing? All right, let's start talking about calculus on this shit. Before I do, I'm going to remind you guys when we had like, we wanted to do ddx of f of g of x. This is a chain rule. We would say u equals g of x. So this is like ddx of f of u. And that's really like a y. This is y here. The whole thing is y. So dy dx equals, well, we have to take the derivative with respect to u first, because that's the variable we had in there. And then the chain rule was do du dx. Chain rule. You may not remember seeing it in this form, but it is one of the forms that it takes. We just did this, something similar. We have a something similar setup with the parameterization. If I want dy dx, and x is a function of t, this ends up being dy dt times dt dx. Similar setup. But dt dx bakes my noodle. I don't operate thinking t in terms of x. I'm thinking x in terms of t. I want dx dt. So if I multiply this effectively by the reciprocal on top and bottom, I get dy dx equals dy dt over dx dt. And that dy dx is the slope of the tangent line. Another way of looking at it is y prime of t over x prime of t. I think that helps because we're going to be looking at things x's and y's in terms of t's. Which leads to some interesting setups. If y prime of t equals 0 and x prime of t does not equal 0, then dy dx equals 0, and we have a horizontal tangent line. If we do y prime of t does not equal 0, but x prime of t does equal 0, we have dy dx equals some value over 0. This is a vertical tangent line. And the fun one is if they're both 0. Well, then dy dx is 0 over 0. And who fucking knows what this looks like? Well, normally we would do something like the L'Hopital or something like that to take it further and see what it looks like, but it may not even work. We can't just make an assumption of what kind of asymptote it is. Or like, not asymptote, but what's going on. Then you got to kind of like analyze what's going on near it, kind of thing. Or plot as y equals f of x, where you might be able to plot it better and see what's going on. And while we're at it, let's find the second derivative. So I'm going to rewrite what we had for dy dx up here. The second derivative looks like this, which is d dx of dy dx. And so this kind of like we had we're effectively applying the d dx on the y prime. And what this ends up looking like is we're going to have d dt of y prime. This is like y is in terms of x right there. When we switch to in terms of t, oops, I need to write in the right notation. Let me make sure I'm saying that right. That looks wrong. Yeah, I don't want to do that. I want to stick with this one up here. That one looks weird. Let me see how a better way of saying this. This is dy prime dt. So y double prime is dy prime of t dt dx. This is the way set it up like we did previously. This leads to dy prime of dt over dx dt, which is d dt. Yeah, I did have it right up there. But this is not, it's better off looking at it at dy dx. Because that's what y prime is. So the way you find the second derivative is find the first derivative. You'll take x prime of t, that's the denominator. Y prime of t is the numerator. And you will get dy dx, y prime of t over x prime of t is in terms of t. And then when you want the second derivative, take d dt of the first derivative and divide by x prime of t from our first calculations. We'll do some examples of this. Let me give you guys like a 10-minute break, a few minutes or something like that. All right, I'll leave that off to the side as we work through some examples here. Let's start off with something simple. Let's let x equal 2t squared plus 1 and y equal 1/3 t cubed minus 1. Nope, minus t. And let's find the equation of the tangent line at t equals 3. Now, before we dive into that, I want to show you just what kind of clusterfuck you're looking at if you try to do this in terms of y and x. So if we solve this for t, we get t equals x minus 1 over 2, and then the square root. And then if we plug it into there, hell no. So now let's not like try to worry about what that's looking like. we weren't asked to find what the graph looks like. We're just asked to find the equation of the tangent line. If we want to see what the graph looks like, to me, in my head, I'm not going to get anything out of plugging this in and trying to figure it out. But I could do t equals 0, 1, 2, 3, and like figure some shit out and graph. We don't need that though. We need dy dx. So we want the tangent line. Tangent line is y minus y1 equals m times x minus x1. And that is dy dx. So if we're going to do it, let's plug it in. We've got dy dx is going to be y prime of t over x prime of t. What's y prime of t looking like? T squared minus 1, right? What is x prime of t looking like? Or t. So dy, we want to find the slope at t equals 3. At t equals 3, dy dx looks like 3 squared minus 1 over 4 times 3. 8 over 12 is 2/3. Now, we could pick any value of x, y that is on this graph. I don't know if t starts at 3 and goes onward, or if t is all for all values t, but I do know that it exists at t equals 3. So let's find x of 3 and y of 3. And that is 3 squared is 9, times 2 is 18, plus 1 is 19. If I do y at t equals 3, I have 1/3 times 3 cubed minus 3. Well, the 3 cubed, 1/3 cancels out one of the 3's. This is 3 squared minus 3. 9 minus 3 is 6. So I will have y minus 6 equals 2/3 times x minus 19. That's the tangent line to whatever clusterfuck of a graph we have at t equals 3. I could. Ugh. Let's see how hard it is. I wonder if I can say t equals square root of x minus 1. I need parentheses there. And then do y equals 1/3 t cubed that is clearly not doing it. Show you what I got going on. Gotta change what I'm sharing over here. So I tried that. So maybe I will copy this. Copy this. Oh shit, it did work. That was the same line. So what time is, what's the X value when T equals 3? Oh shit, X is 19. If I come over and look at where X is 19, it's right here. That is 19.6. And it does look like 2/3 is a reasonable slope there. Let's graph y minus 6 equals 2/3 x minus 19. And look at that beaut. Maybe if I change this to look like a light color and dash it right there, we can see it. Where is it? 19. Yeah. Bam. All right. Enough of that fun. While we're at it, let's take a look at d squared y dx squared. Let's just find it for fun. So what we're doing is we want to take d dt dy dx, and we're going to put it over x prime and t, which we already saw was 4t. Now, I really don't want to do the quotient rule. So what I'm going to do is I'm going to write dy dx t squared minus 1 over 4t. I'm going to write this as t squared over 4t minus 1 over 4t. So dy dx is 1/4 t minus 1/4 t to the negative 1. And now when I take the time derivative of that, I get 1/4 plus 1/4 t to the negative 2, or 1/4 plus 1 over 4t squared. And if I got a common denominator, that would be t squared plus 1 over 4t squared. So if I put that in up here, I don't like having complex fractions, so I'm going to clear them by doing multiplying by the reciprocal of the bottom. I get our second derivative with respect to x, or y double prime, is t squared plus 1 over 16t cubed. That's just to give us some practice doing that. Wait, what? Are we talking about right here? Over here? So what's the question again? I multiplied this first one by t squared over t squared to get a common denominator. Yeah. It's all good. That's what you should do. If you don't know, want to make sure. Always ask. All right, let me give you guys another one. Everyone ready for one? Wait, nope, a couple pins still going. And then kind of like draw a dividing line. What I did was that, got down to here, plugged it back in up there. All right. Next idea, not idea, same idea, new problem. We're gonna have x equal t cubed plus t squared. And y is gonna equal 2 minus t squared. And find dy dx and e squared y dx squared. I'm gonna give you guys a few minutes to do it on your own, then we'll do it together. Make sure everyone's got the first part right. Did everyone get that for dy dx? It's a good idea. In fact, that's a really fucking good idea. I was gonna try to take the time derivative of this without reducing. And that was gonna be a bitch. Oh my God, scrub move up here. If we reduce to this bottom part factors out a t. And this turns into -2 over 3t plus 2. Which is a whole lot easier. And when I want to do the derivative of that, I'm going to write this like that, so I don't need to take the quotient rule. I fucking hate the quotient rule. If you like the quotient rule, go with the quotient rule, but fucking I hate that son bitch. It is not my friend. So when we do the time derivative of that, I bring the power down, it makes it +2, lower the power by 1, and then take the derivative of the inside. I'm getting 6 over 3t plus 2 squared. So if I want d squared y dx squared, I got to do the d dt dy dx on top over dx dt on bottom. I'm getting 6 over 3t plus 2 squared there. On bottom, I'm getting -2 over 3t plus 2 here. Multiply by the reciprocal. I'm getting -3 over 3t plus 2. And that's d squared y dx squared. You guys get that? Was anyone on the second derivative yet? Did I rush too fast? How far did you get, Michael? Oh, yeah. Quotient rules your enemy. I mean, sometimes it's the faster way, but yeah. Oh, shit. Yeah, I done fucked that. I even wrote it. I fucked that up. Good catch. Thank you. We have the 6 over 3t squared, 3t plus 2 squared there. The bottom is 3t squared plus 2t. Ew. If we get a common denominator, it is gonna end up looking like that. Question for you. I could put, yeah, I could have a t times 3t plus 2. That does make it cleaner, doesn't it? Damn it. That's what happens when I don't work the problems out ahead of time. So when I clean it up, I've got 6 over t times 3t plus 2 cubed. That's the cleaner form. Right? That's what. So let's clean it up. That's that. All right, related question. Does this stuff tell us anything about increasing, decreasing regions? Or concavity? How do we find regions of increase or decrease? No, that's concavity. We're like where it's increasing is where like the slope's going to be increasing, right? So we're really looking at like increasing would be where dy dx is greater than 0. And that's dy dx is less than 0. So what does that tell us in terms of the parameterized? Of the parametric version. What is it? What are we finding out here? Well, let's take a look at it. We had dy dx equaled -2 over 3t plus 2 squared. If we're looking for where that's greater than 0, the only spot that's crucial is where the bottom equals 0. T equals -2/3. I have a 0 there. I can't have it. Maybe test -1 and 0 and see what's happening. If I stick in -1 for t, I got -2 over 3 times -1 plus 2. This is positive. And if I stick in 0, I have -2 over 2, which is negative. So what is it telling me? This form tells me for what values of t. Y equals f of x is increasing or decreasing. It's giving us the time frame, not the x values. If you want the actual regions of increasing and decreasing, let's say XY regions, we need to find the values where it shifts. And without having a graph for what this looks like, and I don't know that this is going to look pretty when we do it. That's not really telling me a lot, but I do know the change happens at t equals 2/3. And so we could find the x and y values that that correlates to. I don't want to say values greater than it or less than it because I don't know which direction on the graph the line is actually moving. If t is increasing to the left, then it's like backwards of what we think. So change happens at t equals 2/3, but you have to check the direction of travel. To see if that's corresponds to x greater than x of 2/3. Like we're saying that it goes negative at t equals, wait, that's negative 2/3. Put a negative in there. So one way to check it real quick is, I'll just do the zero version. Let's do the negative 2/3 and the 0. So when x is negative 2/3 or t is negative 2/3, we have negative 2/3 cubed plus negative 2/3 squared. Negative 8/27 plus 4/9. And if I get a common denominator, I get this happening at negative 8 plus 12/27 is 4/27. So the change happens at x equals 4/27. When t is 0, x is 0, which just happens to be to the left. So this is x down here and t up here. So it looks like it's going up as t increases, x goes down. As t goes up, it went from negative 2/3 to 0, went up, x went down, which means like the regions of increase, it's negative over here and positive over here. I'm matching the signs up with the where x of 0 was up here. So I'm grabbing this and matching that up with this. So even though like the slope is negative for time greater than negative 2/3, it actually flips it when we're looking at the XY graph. Backwards. Does that make sense? That's like a complicated idea. I want to make sure that makes sense. So I found my change point here. I tested x equals 0 because I know whatever x equals 0 is to the left here. And it looks like t has gone up. well, not x equals 0, t equals 0. I checked t equals 0 over here. And it happened to lead to x being the opposite direction. So I'm like, it has to flip the graph of that. Does it make sense? To make this look like this graph like this, look like that graph down like there, in terms of the 0 and negative 2/3, I need to flip the sides that say negative and positive. Okay. Yeah. This problem. Sometimes it'll line up perfect, it'll be the same. Yeah. Yes. Maybe it'll help if we look at like t equals -1. Which paper? Yeah, I was gonna leave that one there. So we found when t equals negative 2/3, we got x equals 4/27. We saw when t equals 0, we got x equals 0. And when we got t equals -1, what I plotted up here, x equals, where's my equation? Oh shit, I do need the other. It was, look at that. Also 0, which means this thing is doubling back on itself at different times of t. I don't know what the y value, well, maybe we should find the y values. Fuck it. What was y? Y was 2 minus t squared. So when x equals 4/27, this was t equals negative 2/3. Y has got to equal 2 minus that squared. Four ninths is 18 ninths minus 4 ninths is 15 ninths. So I have 4/27, 15 ninths. That's our turning point. Turning time. What? 14. Because I know how to subtract 18 minus 4. I'm good at this shit, aren't I? Maybe this was worth doing. I made some assumptions that it was going to be true, but looks like we got a graph that turns back on itself. When t equals 0, x equals 0, and y equals 2. And when t equals -1, x equals 0, and y equals 1. So like there's 4/27. At t equals negative 2/3, we are right about there. T equals -1 is up here. And t equals 0 is here. I don't know where it turns, but apparently it's coming along like this. I don't know if it turns right at, it probably does. Turns there. It's going like that. You're right. So my arrows are wrong. Reverse the flow. So this is like kind of interesting. So timeline wise, like we said, it was positive over here, negative over here. For values that were below, it's less, it's got a positive slope, right? As soon as it gets here, it has a negative slope. It doesn't happen to be continuing the same direction, but the slope is still negative. Deep. So it does tell us where the change is happening. It's not all that helpful in terms of the graph, but that'll kind of, apparently whatever this is a sidewards parabola. Maybe not even parabola, there's some other shit going on. We could figure it out if I were to do this one. And I'm not going to, for time reasons. I would say t squared equals 2 minus y. That gets plugged in there. T cubed would be t minus y. What the hell did I just write? 2. There we go. 2 minus y to the 3 halves. I would plug that in there and try to grab it. If I wanted to do that, I'd probably solve for y, and I don't know that that's easy to fucking do. We got 10 minutes left. I do want to tell you about arc length and surface area. Definitely arc length. And I'll show you surface area. Probably won't have a problem with surface area on the test. So arc length. What's our old formula for arc length? What is this? F prime of x squared. And we're going from a to b of dx. I don't want to write it like that. That is what it is. But I'm going to write this as 1 plus dy dx squared. Dx. When we switch to t, what's going on? T1 to T2, or start point to end point, basically. dy dx was dy dt over dx dt. I'm trying to show you a way that you can always pull the new formula out from the old one. So if I do some manipulation here. Oops. T2 to T1. I can get a common denominator, multiply this by dx dt squared. And I'll have dx dt squared on bottom. Plus dy dt. Still got a dx. And I'm going to split that square root thing to have the square root of the top separate of the square root of the bottom. The square root of the bottom, I can just take the square root, is dx dt. And again, this this shit doesn't really happen this way, but it totally works. If I wanted to clear fractions, it kind of looks like that goes away and that goes away. And we're left with the arc length in the parametric form is dx dt squared plus dy dt squared. The square root of that dt. This isn't exactly what's happening the same way when we do like dy dx and we do like a u sub, we'll say like du dx and we'll have du on one side and dx on the other. It looks like you're multiplying by dx. You're not. This is like doing like a differential form kind of thing, but the result looks the same. And surface area format, like the surface area revolution. When we're rotating around y, our old form was, I'll use alpha and beta this time, was 2 pi x ds. And this is turning into t1 to t2 of 2 pi x of t ds. Where ds equals this. When we originally derived arc length, that's what we called this. The square root was the ds, where ds is the square root of dx dt squared plus dy dt squared. When you're rotating around x, again, the area alpha to beta was 2 pi y ds. So when we turn it to time, it's going to be t1 to t2. Two pi y of t, then our ds, square root of dx dt squared plus dy dt squared dt.
Does that mean the ES, that has PT attached to it as well?
Yes. Thank you. Now, we are out of time, but I'm gonna put up two problems. Try to work them out. I will write out the solutions and load them up probably tomorrow. I'll write them out tomorrow. The first problem is gonna be relating to what we had previously, the areas of increase and decrease. Show that the curve x equals t squared minus 3t plus 5 and y equals t cubed plus t squared minus 10t plus 9 intersects itself at the point 3,1 and find equations for the two tangent lines. At the point of intersection. I'm going to give you a hint on how to start. Hint. You know the x value when they intersect. Find the t's that go with it. That'll give you the 2 points of time it happens. And then the other one I will walk through, do on another piece of paper. We're going to have x equals 3t minus t cubed. Y equals 3t squared. And we're going to go from 0 less than t or equal to t, less or equal to 1. We will find the surface area obtained when the curve is rotated about the x-axis. I know that should have a solution. Arc length might, but the derivative of this might make it shitty, and I don't want to say that it does, but the surface area should. And I will walk through some solutions for both of those. It's 5 o'clock though, 6 o'clock, so have a good evening.